Welcome to Physics for Life. This is a quick revision video of chapter Wave Optics. So, nature of light. The phenomena like interference, diffraction, and polarization establish the wave nature of light. However, the phenomena like black body radiation and photoelectric effect establish the particle nature of light. De Broglie suggested that the light has a dual nature, means it can behave as a particle as well as wave. Wavefront. A wavefront is defined as the continuous locus of all such particles of the medium which are vibrating in the same phase at any instant. In case of waves traveling in all directions from a point source, the wavefronts are spherical in shape. When the source of light is linear in shape, then the wavefronts are cylindrical. At a very large distances from the source, a portion of spherical or cylindrical wavefront is a plane wavefront. Now ray. An arrow drawn perpendicular to a wavefront in any direction of propagation of wave is called a ray. Two general principles are valid for rays and wavefronts. First is rays are normal to wavefronts, and second is the time taken to travel from one wavefront to another wavefront is same along any ray. Now next is Huygens principle of secondary wavefront. Huygens principle is the basis of wave theory of light. It tells how a wavefront propagates through a medium. It is based on the following assumptions. First, each point on the wavefront acts as a source of new disturbance called secondary waves or wavelets. Second, the secondary wavelets spread out in all directions with the speed of light in the given medium. Third, the wavefront at any later time is given by the forward envelope of the secondary wavelets at that time. Now next is effect on frequency, wavelength and speed during refraction. When a light travels from one medium to another, its frequency remains unchanged, but both its wavelength and speed get changed depending on the refractive index of the refracting medium. Now next is interference of light waves. When light waves from two coherent sources traveling in the same direction superpose each other, the intensity in the region of superposition gets redistributed, becoming maximum at some points and minimum at other points. This phenomenon is known as interference of light. Now next is constructive and destructive interference. So if path difference p is equals to nv, or phase difference phi is equals to 2n pi, the two waves are in same phase and so add up to give maximum of intensity. This is called constructive interference. And now if p is equals to 2n minus 1 into lambda by 2 or phi is equals to 2n minus 1 into pi, the two superposing waves are out of phase. The resultant amplitude is equal to difference between their individual amplitudes and hence the intensity is minimum. This is called destructive interference. Now next topic is Young's double slit experiment. So in Young's double slit experiment, two identical narrow slits S1 and S2 are placed symmetrically with respect to narrow slit S illuminated with a monochromatic light. The interference pattern obtained on an observation screen placed at a distance capital D from S1 and S2. The position of nth bright fringe from the center of screen, that is xn is equals to n into d lambda by small d, and the position of nth dark fringe from the center of the screen is x dash n is equals to 2n minus 1 into d lambda by 2 small d, and beta is equals to d lambda by small d, that is the fringe width is the separation between two successive bright or dark fringes, and it is given by this. Now next is resultant amplitude and intensity of interfering. So if A1 and A2 are the amplitudes of I1 and I2 are the intensities of two coherent waves having phase difference phi, then their resultant amplitude and intensity at that point of superposition are given by A is equals to under root A1 square plus A2 square plus 2 A1 A2 cos phi, and I is equals to I1 plus I2 plus 2 under root I1 I2 cos phi. And if the amplitude of each wave is a naught and intensity is I naught, then I is equals to 2 k a naught square in the bracket 1 plus cos phi, which is equals to 2 I naught in the bracket 1 plus cos phi, is equals to 4 I naught cos square phi by 2. The term 2i1 under root i1 i2 cos phi is called interference term. And first, when cos phi remains constant with time, the two sources are coherent. The intensity will be maximum at the points for which cos phi is equals to plus 1 and minimum at the points where cos phi is equals to minus 1. And second, when cos phi varies continuously with time, so that its average value is 0 over the time interval of measurement, the resultant of intensity at all points will be I1 plus I2. No interference fringes are observed. The sources are incoherent. Now next is ratio of intensity at maxima and minima of an interference pattern. If A1 and A2 are the amplitudes of two interfering waves, then the ratio between the intensities at maxima and minima will be I maximum upon I minimum is equals to A1 plus A2 whole square upon A1 minus A2 whole square, which is equals to R plus 1 upon R minus 1 whole square. And where A1 upon A2 is equals to under root I1 upon I2 is the amplitude ratio of the two waves, and where this W1 upon W2 is equals to I1 upon I2, which is equals to A1 square upon A2 square. Here this W1 and W2 are the widths of the two slits. Now next is coherent sources. Two sources of light which continuously emit light waves of the same frequency or wavelength with a zero or constant phase difference between them are called coherent sources. Two independent sources of light cannot act as coherent sources. They have to be derived from the same parent source. Now next is conditions for sustained interference. First is the two sources should continuously emit waves of the same frequency or wavelength. Second, the two sources of light should be coherent. Third, the amplitudes of the interfering wave should be equal. Fourth, the two sources should be narrow. Fifth, the interfering waves must travel nearly along the same direction. Sixth, the sources should be monochromatic. Seventh, the interfering wave should be in the same state of polarization. And eighth, last one is the distance between the two coherent sources should be small, and the distance between two sources and the screen should be large. Now next is Frenzel's biprism method. Here two coherent sources are obtained from an incoherent source by refraction. A biprism is essentially a single prism with an obtuse angle of 179 degree, but behaves as a combination of two acute angled prisms placed base to base, each with a refracting angle of about 1 by 2 degree. Now next is Light's single mirror method. In this method, an illuminated slit and its reflected image serve as two coherent sources, in contrast to Young's double slit and Frenzel's biprism method. Here the central fringe is dark. Now next is displacement of interference fringes. When a thin transparent sheet of thickness t and diffractive index mu is inserted in the path of one of the interfering beams, the extra path difference introduced is delta p, which is equals to length t in the transparent sheet minus length t in the air. So delta p will be equals to mu t minus t, which is equals to mu minus 1 into t, and therefore the net path difference for any point on the screen will be equals to xt upon capital D minus mu minus 1 into t. And for the central points on the screen, xt upon capital D minus mu minus 1 into t is equals to 0, or x is equals to d by small d mu minus 1 into t. Thus the shift is the central bright fringe, and hence shift of any other fringe is del x is equals to capital D upon small d mu minus 1 into t is equals to beta upon lambda mu minus 1 upon t. Now next is interference in thin films. So a soap film or thin film of oil spread over water shows beautiful colors when seen in the reflected light. This is due to the interference between light waves reflected by the upper and lower surfaces of the thin films, and the ray reflected from the upper denser surface of the thin films suffers a phase change of pi or path difference lambda by 2. So reflected system. The path difference between the two consecutive rays reflected from the upper and the lower surfaces of a thin film of refractive index mu and thickness t is given as p is equals to 2 mu t cos r minus lambda by 2. And for maximum intensity 2 mu t cos r is equals to 2n plus 1 into lambda by 2. And for minimum intensity 2 mu t cos r is equals to n lambda. And now transmitted for a transmitted system, maximum intensity will be 2 mu t cos r is equals to n lambda, and for minimum intensity 2 mu t cos r is equals to 2 n plus lambda n plus 1 into lambda by 2, where n is equals to 0 1 2 3 up to infinity. Now next is diffraction of light. The phenomenon of bending of light around the corners of small obstacles or apertures and their consequent spreading into the regions of geometrical shadow is called diffraction of light. Diffraction at a single slit. So a plane wave of wavelength lambda on passing through a narrow slit of width a suffers diffraction, producing a central bright fringe theta is equals to 0 degree at and flanked on both sides of maxima and minima. The intensity of secondary maxima decreases with increase in the distance from the center. So this is the expression a sine theta n is equals to n lambda is for nth minimum, and where n is equals to 1 2 3 up to infinity, and for nth secondary maximum a sine theta n is equals to 2n plus 1 into lambda by 2. And angular position of nth minimum theta n is equals to n lambda by a, and distance of nth minimum from the center of screen xn is equals to n d lambda by a, and angular position of nth secondary maximum theta dash n is equals to 2n plus 1 into lambda by 2a, and the distance that is x dash n is the distance of nth secondary maximum from the center of screen, which is equals to 2n plus 1 into d lambda by 2a. Now beta that is width of a secondary maximum is equals to d lambda by small a, and width of central maximum beta dash beta naught minus 2 beta is equals to 2 d lambda by a, and angular spread of central maxima on either side of the center of the screen, that is theta is equals to plus minus lambda by a, and this expression 2 theta is equals to 2 lambda by a is for total angular spread of the central maximum. And for the diffraction to be more pronounced, the size of the slit should be comparable to the wavelength of light used. And diffraction at a circular aperture. So for the diffraction of light at a circular aperture of diameter a, the angular spread of central maximum is theta is equals to 1.22 lambda by a. If capital D is the distance at which the effect is observed, then linear spread x is equals to d theta, and areal spread x square is equals to d theta whole square. And now next is Fresnel's distance. So it is the distance at which the diffraction spread of a beam becomes equal to the size of the aperture. If a is the width of the aperture, then d f is equals to a square by lambda. The ray optics is valid for distance d is less than df. Now diffraction grating. So it is an arrangement of a very large number of very narrow equidistant and parallel slits. The diffraction pattern has the central principal maximum of maximum intensity and a number of higher order intensity maxima whose intensity decreases with the increase of n, the order of spectrum. The direction of nth principal maximum is given as a plus b into sine theta n is equals to n lambda, where n is from 0, 1, 2, 3 up to infinity. This equation is known as the grating law. Here a plus b is called grating element, where a is the width of each slit and b is the width of opaque space between two consecutive slits. Now next is limit of resolution. So the smallest linear or angular separation between two point objects at which they can be just resolved by an optical instrument is called the limit of resolution of the instrument. Now next is resolving power. It is the ability of an optical instrument to resolve or separate the images of two nearby point objects so that they can be distinctly seen. It is equal to the reciprocal of the limit of resolution of an optical instrument. Now next is diffraction as a limit on resolving power. So all optical instruments like lenses, telescopes, microscopes, etc. Act as aperture. Light passing through them undergo diffraction. This puts the limit on their resolving power. Rayleigh's criterion for resolution. So the images of two point objects are just resolved when the central maximum of the diffraction pattern of one falls over the first minimum of the diffraction pattern of other. Now next is resolving power of a microscope. So the resolving power of a microscope is defined as the reciprocal of the smallest distance d between two point objects at which they can be just resolved when seen in the microscope. So resolving power of a microscope is equals to 1 by d, which is equals to 2 mu sine theta upon lambda, where this theta is the half the angle of the cone of light from each point object, and mu is the refractive index of the medium between the object and the objective. So now the factor this mu sine theta is called numerical aperture. Now next is resolving power of a telescope. So resolving power of a telescope is equals to 1 by d theta, which is equals to d upon 1.22 lambda. The resolving power of a telescope is defined as the reciprocal of the smallest angular separation, that is d theta, between two distant objects whose images can be resolved by it. And here this d is the diameter of the telescope objective, and lambda is the wavelength of light used. Now next is resolving power of the human eye. The human eye can see two point objects distinctly if they subtend at the eye an angle equal to 1 minute of arc. This angle is called the limit of resolution of the eye. The reciprocal of this angle is equal to the resolving power of eye. Now next is polarization of waves. Transverse wave in which vibrations are present in all possible directions in a plane perpendicular to the direction of propagation is said to be unpolarized. So if the vibrations of a wave are present in it in just one direction in a plane perpendicular to the direction of propagation, the wave is said to be polarized or plane polarized. So the phenomenon of restricting the oscillations of a wave to just one direction in the transverse plane is called polarization. Now next is unpolarized light, a kind of light in which the electric field vector vibrations in all possible directions in the transverse plane rapidly and randomly during the time of measurement is called unpolarized light. For example, the light of the sun, candlelight, etc. Now next is PPL, that is plane polarized light. So if an electric field vector vibrates just in one direction perpendicular to the direction of the wave propagation, the light is said to be linearly polarized. In a linearly polarized wave, the vibrations at all points at all times lie in the same plane. So it is called a plane polarized wave. Now next is polarizer, a device that polarizes the unpolarized light passed through it is called polarizer. For example, Tor tourmaline crystal, nickel prism, and a Polaroid, etc. Now, law of Malus. This states that when law of Malus. This law states that when a beam of completely plane polarized light is passed through an analyzer, the intensity I of the transmitted light varies directly as the square of the angle theta between transmission directions of polarizer and analyzer. So I is equals to I naught cos square theta, where this I naught is the maximum intensity of the transmitted light. Now next is plane of polarization. So the plane passing through the direction of wave propagation and perpendicular to the plane of vibrations is called plane of polarization. Plane of vibration. So the plane containing the direction of vibration and the direction of wave propagation is called the plane of vibration. Now next is Brewster angle. The angle of incidence at which a beam of unpolarized light falling on a transparent surface is reflected as a beam of completely plane polarized light is called polarizing or Brewster angle, and it is denoted by I small I p. Now next is Brewster law. So this law states that the tangent of the polarizing angle of incidence on a transparent medium is equal to its refractive index. So mu is equals to tan I p. Now next is nickel prism. So it is an optical device based on the phenomenon of double refraction, which is used for producing and analyzing the plane polarized light. It consists of two pieces of calcite cut with angle 68 degree and stuck together with Canada ballism. So now next is Polaroids. So these are the thin commercial sheets which make use of the property of selective absorption to produce an intense beam of plane polarized light. Polaroids are used in sunglasses, camera fibers, wind screens, and car headlights of motor cars to reduce a glare of the light reflected from shiny surfaces, etc. Now next is optical activity. Substances which can rotate the plane polarized light are called optically active substances. So while the phenomenon is called optical activity. Now next is specific rotation. So it is the angle through which the plane polarization rotates when plane polarized light is passing through 1 decimeter length of solution containing 1 gram of substance per centimeter cube. So the measurement is done at temperature T using sodium light, the D line. So specific rotation is equals to here the theta upon L into C. Theta is observed angle of rotation in degrees, and L is the length of the tube in decimeter, and this C is grams of substance in 1 centimeter cube of solution. Now next is Doppler effect. So it is the phenomenon of the apparent change in the frequency of light due to the relative motion between the source and observer. The apparent frequency V dash is given by V dash is equals to V in the bracket 1 plus minus V upon C. So the source moved towards the observer, the velocity V is taken as positive, and when source move away from the observer, then V is taken as negative. Now last topic is Doppler shift. The apparent change in the frequency of light due to Doppler effect is called Doppler shift. First, there are two formulas. First is del V is equals to plus minus V by C nu. This is nu. And next is del lambda, which is equals to plus minus V by C into lambda. Thank you for watching the video.